Okay, good day everyone. I am Mr. Franklin P. Calaminos, a PhD Math Ed student of Sorsogon State University School of Graduate Studies. Now let me discuss to you the topic while ordering principle, completeness axiom, and Archimedean property. So this is under the subject real analysis. Now let me start with well ordering principle. So based on its definition, a non-empty subset S of R is well ordered if every non-empty subset of S has the smallest element. Okay, so one of the conditions to be satisfied is it should be non-empty subset. And the second is, okay, so that subset S from R contains the smallest element. Or in other words, we can easily identify the smallest element of such subset. So let's have an example. So as stated, we have here the set of natural numbers. So it is considered well ordered. Why? Since we knew that the set of natural numbers is equivalent to, or that is equal to, the set of positive integers, in which that set, okay, starts with 1 up to positive infinity. So from that, it contains the smallest element, or we can easily identify the smallest element, which is positive 1, or simply 1, as an element of the set of natural numbers. So that is the reason why it is considered well ordered. Next, we have the following sets, which are also considered well ordered. But as you can see, those examples involve the set of natural numbers. So let's try to test whether if that will be union with the other subsets or sets. So do you think it will affect, okay, whether it is well ordered or not? So let's have number 1. Although, as stated, these are well ordered sets. So again, for number 1, you have the union of the set of natural numbers with 0. Okay, so instead of 1 as the smallest element, since that is union with 0, so still that is well ordered since it contains the smallest element, which is now equal to 0. Next, we have the set of natural numbers having the union with negative 1 and 0. So here, we just replace 0 as the smallest element with negative 1. Okay? Still, that is well ordered. Then for number 3, we have again the set of natural numbers union with negative 3, negative 2, and negative 1. So here, again, that contains the smallest element, which is negative 3. Instead of negative 1, 0, and 1 on the previous examples. Okay? Then for number 4, we have, okay, a natural number, which is an element of the set of natural numbers. Okay, so those are denoted by lowercase letter, okay, which is an element of the set of natural numbers denoted by uppercase letter n, in which n, okay, should be greater than 5. Okay, or that simply means that we are after with the elements, okay, which are natural numbers greater than 5. So start with 6 up to positive infinity. So from that, we can easily identify the smallest element. So instead of 1, okay, as the smallest element of the set of natural numbers, since we have the criterion or the restriction that n should be greater than 5, so here On such case, the smallest element is 6. Okay? So again, those are well-ordered sets. What about the non-well-ordered set? So for number 1, we have the set of real numbers. Okay, particularly the open interval from 0 to 2. Okay, so we knew that if we have an open interval, those boundaries 0 and 2 are excluded. Okay, so we will be after with the values between 0 and 2, but the values, okay, between 0 and 2 are infinite, since we have to consider the set of real numbers. So with that, we cannot easily identify the smallest element. Okay, so that is the reason why it is not well ordered. For number 2, we have the set of negative integers. Okay, so both 1 and 2 are non-empty subset, but it doesn't satisfy, okay, the second condition, having the smallest element. So for number 2, again, okay, it doesn't contain the smallest element. Why? Since if we are dealing with negative integers, okay, so the greatest integer is -1, but we are after with the smallest, and we knew that the trend of the values on the set of negative integers is decreasing. And if we're going to consider the set of negative integers that starts from -1 to -infinity, so with that we cannot identify, okay, the smallest element, since, okay, it is up to -infinity. Then lastly, we have the interval, the closed interval 0 to 1. Why close? Since you have used here pair of brackets, although, okay, that is not well ordered. Why? Since it contains a non-empty subset, okay, which is an open interval from 0 to 1. So this is an similar, okay, to the open interval that we have considered on number 1, having the set of real numbers. And we knew that between 0 and 1, there are infinite values, so we cannot easily identify the smallest element, or it doesn't contain the smallest element. So with that, okay, so these 3 examples, okay, the last 3 examples are considered not well ordered. Again, it for the given set or subset to be well ordered, it should contain, okay, the smallest element and a non-empty subset. Okay. Okay. Now, for the next definition, this is in particular with the set of integers with the application of well-ordering principle. So it states that let B be a set of integers. Then an integer M is called the least element of set B. Okay, if M is an element of B, and for every X in B, M is less than or equal to X. Okay, so since M is the least element, okay, so that is the reason why on the last part of the definition, okay, it is included that M is less than or equal to X. Okay, now for the first example, in line with the given definition, so you have 3 as the least element of the set 4, 3, 5, and 11. So if we're going to observe the given elements on such set which contains 4 elements, so 3 is considered the least element. Okay. For number 2, we have let A be the set of all positive odd integers, then 1 is at least or a least element of A. Okay? So, aside from being a positive integer, it should be an odd integer. Okay? So, we knew that an odd integer are integers or numbers that are divisible by 2 with a remainder of 1. And among those odd integers and positive at the same time, 1 is the least element. Okay? Then what about, for example, number 3? We have let U be the set of all odd integers. Okay? So, then U has no least element. Okay? So, why is that it has no least element? Okay, since we have all odd integers. So, that includes both positive and negative integers. So, if we're going to compare example 2 with example 3, so for example 2, we have only considered the positive odd integers, and we can easily identify, or it contains the least element, which is 1. Then for number 3, since it involves not only positive but also negative, and we knew that the trend of the values on a set of negative integers is decreasing from negative 1, okay, up to negative odd integers, okay, particularly, so it doesn't contain the least element. Okay, so that is the reason why. Okay, so for number 3, that is the only set in which we cannot identify the least element, or it doesn't contain the least element. Okay, so we are done with the well-ordering principle. So let's have now the completeness axiom. So here, okay, particularly we are going to discuss bounded and unbounded sets. So let's have first its definition. So let S be a non-empty subset of R, in which on letter A, the set S is said to be bounded above if there exists a number U, element of real numbers or the set of real numbers, such that S is less than or equal to U for all S element of S or set S. Now, each such number U is called an upper bound of S. Okay, so that is how we define bounded above. Okay, and as well as the upper bound of S. Okay, so next for letter B, the set S is said to be bounded below if there exists a number W, element of the set of real numbers, such that W is less than or equal to S for all S is an element of the set S, and each such number W is called the lower bound of S. Okay, so for letter B, we are after with bounded below and the lower bound of S. Then for letter C, a set is said to be bounded, okay, which is both bounded above and bounded below. So it means that it satisfies the conditions for letter A and letter B for being bounded above and bounded below. So for letter C, okay, for us to consider that the set is said to be bounded, so it should satisfy both conditions. Okay, so a set is said to be unbounded if it is not bounded. Okay, so that is how we differentiate bounded from unbounded sets. Okay, so for us to further understand, okay, those definitions presented regarding bounded and bounded sets. So let's have, okay, examples. So on this slide, we have three sets. So for S, okay, that is the set of all x such that x is an element of the set of real numbers, okay, having the criterion that x should be less than 2. Okay, so we'll be identifying whether it is bounded above, okay, or bounded below. So based on the first row, okay, we have bounded above, okay, and since that is bounded above, okay, so the upper bound of such set, okay, based on the definition, so we have x that is greater than or equal to 2, okay, so the upper bound starts from 2, okay, up to positive infinity. Then if we will be asked if it is bounded below, okay, so the answer is no. Therefore, it doesn't contain lower bound. Okay, so on the next column, okay, so we will be identifying whether the first set is bounded or unbounded. Okay, so obviously the answer is unbounded. Okay, why? Since it only satisfies, okay, being bounded above, and the upper bound, okay, starts from 2 to positive infinity. Okay, so again, the first set is said to be unbounded. Now let's have S sub 1, in which that is the set of all x such that x is an element of the set of real numbers in which x is greater than or equal to 0. Okay, so it is not bounded above, therefore, okay, doesn't contains upper bound, while it is bounded below, okay, and it contains the lower bound that starts from 0 to negative infinity. Okay, so as stated, x is less than or equal to 0. So with that, it is unbounded since it only satisfies the conditions of being bounded below. Okay, now let's have S sub 2, which is said to be bounded. Okay, so with that, it satisfies both conditions of being bounded above and bounded below. Okay, so let's have first the given set. Okay, so that is the set of all x such that x is an element of the set of real numbers. So we have here a continued inequality, okay, in which x is greater than negative 2 but less than positive 2. Okay, so it is bounded above, in which the upper bound starts from 2 to positive infinity, while the lower bound, okay, starts from negative 2 to negative infinity. Okay, since as stated, x is less than or equal to negative 2. So therefore, it is both bounded above and bounded below. Okay, and that is the reason why it is considered bounded. Okay, so as you can see, as mentioned a while ago, okay, we can only consider, okay, a set, okay, to be bounded if both conditions, okay, being bounded above and bounded below are satisfied. Okay. Okay, so on this slide, okay, we have here an illustration in which we can differentiate, okay, upper bounds and lower bounds of S in connection with the next subtopic to be discussed, which is all about the supremum and infimum. Okay, so as you can see here on the right side of set S, okay, we have the upper bounds of S, okay, which starts from this point, okay, from the supremum of S, okay, to positive infinity, okay, or to the right. While the lower bounds of S is located on the left side, okay, in which starts with the infimum of S up to the values on the left side, or to the negative infinity, if that will be put on the real number line. Okay, so that is how we illustrate the upper bounds and the lower bounds of a particular set, which is denoted by S. So here on the illustration, we have already encountered the supremum and the infimum of S. Now, let's have the formal definitions of these two terms. Okay, so according to its definition, so let S be a non-empty subset of the set of real numbers, in which if S is bounded above, then a number U is said to be a supremum or a least upper bound of S if it satisfies the conditions. Number one, if U is an upper bound of S, okay, so U should be a member or an element of the upper bound of S. So we cannot consider supremum which is excluded from the upper bound of S. Okay, so for number 2, if V is any upper bound of S, then U, okay, should be less than or equal to V. Since U is the least upper bound, okay, therefore the values on the right side of U, okay, are greater than U, which is the least upper bound. So that is shown on the illustration a while ago on the previous slide. Okay, so starts with U, okay, up to, okay, the values on the right side of U, which are greater than U. So in symbols, okay, so that is U is less than or equal to V. Okay, next, if S is bounded below, then a number W is said to be an infimum or a greatest lower bound of S if it satisfies the conditions. Number 1, W is a lower bound of S. Okay, so again, it should be an element or a member of such bounds. Okay, particularly the lower bounds of S. Then for number 2, if T is any lower bound of S, then, okay, T is less than or equal to W. Okay, or that is W is greater than or equal to T. Okay, since based on the illustration, so we start with W, then on the values located on the left side of W, okay, which is represented by T, and those values are less than or could be equal to W. So that is the reason why we have here, okay, the second condition, okay, as stated on its definition, okay, for an infimum or the greatest lower bound. Okay? So that is how supremum and infimum are defined. Okay? So let's go back to the given examples a while ago and let's try to identify whether those sets, okay, have supremum and infimum. Okay, so again, for the first set, we have kx is an element of the set of real numbers and x is less than 2. So a while ago, we have identified that it is bounded above. Okay, so with that, okay, it contains a supremum. Okay, and the least upper bound of such set, if that set contains supremum, okay, is 2. Okay, since we have the upper bound, that is x is greater than or equal to 2. Then for its infimum, okay, so that is negative infinity. Okay, so it doesn't contain uh, lower bounds, okay, since that is not bounded below. Okay, and also one of the reasons why we cannot expect that it contains both supremum and infimum, so we have concluded a while ago that it is unbounded, okay, or that is only bounded above. Okay, so why is that 2, okay, is not considered a maximum? When we say maximum, okay, so it should be included as one of the elements on the given set. Since we have this restriction or criterion that x is only less than 2, so therefore it is not considered as a maximum. Okay, so only a supremum of s, okay, as the least upper bound. Then what about for s sub 1? Okay, or the second set in which the criterion is x is greater than or equal to 0. So a while ago we have identified that it is bounded below. Okay, and having the lower bounds, x is less than, okay, or equal to 0, and again that is unbounded since it is only bounded below. Okay, so with that, for its supremum, that is positive infinity, while for the infimum, okay, so that is exactly equal to 0. Okay, and that is considered the minimum of set S. Why it is considered minimum? Since we have here having not only greater than to 0 but equal to 0. So it is included as one of the elements of set X, or yes, set X. Okay, or rather S sub 1. Okay, so let's have S sub 2, that is having the criterion that x is greater than negative 2 but less than or equal to positive 2. So this is both bounded above and bounded below. So with this, okay, we can both identify the supremum and infimum, or those values are said to be exact. Okay, so again, this is a bounded set. Okay, so the supremum is 2. Okay, and this is considered maximum. Unlike with set S, okay, so 2 is excluded as member or as an element of set S. So with that, okay, that is not considered maximum. So here for S sub 3, since it is included as an element of set S sub 2, so this is maximum of set S. Okay? What about for its infimum? Obviously, that is negative 2. Okay? As the first element, okay, or that is characterized as the greatest lower bound of set S. Okay? Or particularly S sub 3. So this is not a minimum. Why? Okay? So again, we have here, okay, a strict inequality. So that is only greater than negative 2 or that is less than x. Okay, we will start considering negative 2 to x. Okay, so again, that is how we identify the supremum and infimum of a particular set, considering those definitions and conditions that we have encountered a while ago on the previous slides. So those are the conditions to be satisfied so that we can identify the supremum and the infimum. Okay, so in line with supremum and infimum, so first of all, it needs to be emphasized that in order for a non-empty set S in R to have a supremum, it must have an upper bound. Okay? Thus, not every subset of R has a supremum, and similarly, not every subset of R has an infimum. So these observations, okay, or these statements were reflected on the given examples a while ago. Okay, and also it was given emphasis on its definition for the supremum and infimum of set S. So we cannot have a supremum, okay, a definite supremum of S if the given set has no upper bound. So the same with infimum. Although, okay, it must have a lower bound. Okay, so we can only have a definite infimum if it contains, okay, lower bounds. Now, indeed, there are four possibilities for a non-empty subset S of R. Okay, so from those examples that we have encountered a while ago, so we have already some of those possibilities. So for number 1, so have both a supremum and an infimum. Number 2, have a supremum but no infimum. Then number 3, we have an infimum but no supremum. Then lastly, we have neither a supremum nor an infimum. Okay, so here we have a theorem in which states that in any non-empty subset of R that is bounded above has a least upper bound. Okay, so this is one of the statements, okay, that we have encountered a while ago, okay, as one of the observations on the given examples. Okay, and as well as one of the conditions to be satisfied, okay, for us to have a supremum. So we cannot have a least upper bound unless it is bounded above. Okay, so that is the same with infimum. Okay, or particularly on a set which is bounded below. So it contains the greatest lower bound. Okay, so in other words, the completeness axiom guarantees that for any non-empty set of real numbers S that is bounded above, a supremum exists. Then analogous property holds for infimum of S. In an empty subset of R that is bounded below, okay, so it has greatest lower bound. Okay, so that was mentioned a while ago. Okay, although we are after with the greatest lower bound when it comes to infimum of S, that the given set should be bounded below. Okay, so that is how we apply the completeness axiom in line with infimum and supremum, okay, of the given set. Okay, so if we're going to go back on the given examples, so we have here the three possibilities, okay, for the three given sets. So for S or set S, okay, so this is the possibility having a supremum but no infimum. For S sub 1, this is the possibility, okay, of having an infimum but no supremum. Then on S sub 3, we have, okay, this is both having a supremum and infimum. Okay. Okay, so on this slide, we have a set of exercises in which you can practice how to determine, okay, whether the given set or subsets of particular set, okay, which is the set of real numbers, are well ordered or not. Well, for letter B, okay, your task to determine if it is bounded above, or bounded below, or both for each subset of R. Then if it is bounded above, okay, so definitely you're going to determine the supremum. Then if it is bounded below, you're going to determine the infimum. So you need to include also your justifications, okay, for your conclusions. So here on the next slide, we have the Archimedean property. So it is defined as the property of the set of real numbers that for any real number, there is always a natural number greater than that real number. Okay, so if that will be stated in a theorem, okay, so if x is an element of the set of real numbers, then there exists n, okay, n sub x, element of the set of natural numbers such that x is less than n sub x. Okay, so that is in line with the definition that we have a while ago, okay, in which again the property of the set of real numbers that for any real number there is always a natural number greater than that real number. So that is the reason why that involves not only the set of real numbers but also the set of natural numbers. So that is how Archimedean property is defined. So from those definition and theorem that we have encountered a while ago in line with Archimedean property, we have some corollaries. So one is if S is equal to 1 over n, where n is an element of the set of natural numbers, then the infimum of set S is equal to 0. Okay? Then the second corollary, we have if t is greater than 0, there exists n sub t, element of the set of natural numbers such that 1 over n sub t is greater than 0 but less than t. Well, the third corollary states that if y is greater than 0, there exists n sub y, element of the set of natural numbers such that n sub y minus 1 is less than or equal to y, okay, and y is less than n sub y, okay. So those are the corollaries, okay, in line with the theorem and as well as on the definition of Archimedean property, in which that involves not only the set of real numbers, but in particular we have the set of natural numbers. Okay, so again, uh, that is all about the well-ordering principle, the completeness axiom, and Archimedean property as one of the topics in real analysis. Once again, this is Mr. Franklin P. Calaminos, a PhD Math Ed student of Sorsogon State University School of Graduate Studies. Thank you for listening and stay safe always.